Hello everyone. So having seen some kind of rules to build Zbus, we have actually seen two rules in the previous videos. So now we come to numerical examples on bus admittance metrics. So in this video, I would like to solve some 4, 5 or 6 problems, and each problem as you solve it, you will get more understanding of how to form the Ybus. And forming a Ybus is the first step, and it's very important step in in solving the load flow problem. So therefore, I hope this video will be useful. So already you can see one question on the screen, that is form Y-bus for the following three bus system. So a simple three bus system is given. This could be, the basic, the starting level, first level problem. So a three bus system is given, and between bus 1 and 2 there is a line whose impedance is J 0.1 per unit. So there is no resistance given, only the reactance. So the resistance is been neglected. So you can also have some resistance. And then there is another line between 2 and 3 whose impedance is J zero point 0.2 per unit. So you can apply your rules and then form the Y bus. You can attempt it, and you can check with my answer. You can pause the video now, and I'll be doing the answer myself. Okay, so what is the answer? Now you know that there are three bus system, so our n equal to 3, that is the size of the system. So therefore, the size of the Y bus will also be 3 by 3 Y bus. So let's have a 3 by 3 Y bus. So it always helps if I just mark the rows and columns like this. Now, this is my habit of doing it. So now I have this as the first row, first column, second column, and third column. First column, first row, second row, and third row. Let's look at the off diagonal element. So what are the rules? So rule 1 and rule 2. So we have learned two rules to form Y bus in the previous videos. So capital Ij is nothing but minus Yij. So and then rule 2 is Yii is nothing but summation of capital Yij. So where j equal to 1 to n and j not equal to I. So if you understand this notation, just sum of the all off diagonal elements in each row will be the I. So let's apply rule 1. So what is Y21? So sorry, Y12. First row, second column. This is the first row and second column. So already the information given to you is impedance. How do you know it is impedance? Because the J is positive, you can tell that this is impedance. So convert into admittance. So what is Y12? So this is Z12. So 1 by J point 1, so it will be minus J10. And this is Z23, or I'll get Y23 equal to minus J5. Because 1 by J point 2, so 1 by point 2 is 5 and 1 by J is minus J. So here I got these values. And so minus of minus J10, so this will be J10. And minus of, I think here I forgot mention minus here. So minus of minus J5 will be, I'm sorry, there's no line between 2 and 3, so 1 and 3, so therefore this element will be 0, and I just simply copy this, and then I copy this row into this column. Now what is the element between 2 and 3? So 2 and 3 I have j minus j5, minus of minus j5 will be j5, and this will be j5. Then now coming to the diagonal element, just add these two. So j10 plus 0, and so that will be j10, and then put a minus sign. So minus j10. Similarly, add these two, j10 plus j15, sorry, j5 is j15, so minus sign, so minus j15. And finally add these two, so it will be minus j5. So that's it. So this is the Y bus for this particular small system. So very easy, you can just look at it and then write it. Okay, let me just slightly change this and then show you what happens. So let's call this example 2. So So for the system like this, so this is Z1, I'm sorry, this is J.1 and this is J.0, sorry, J.2. So it's the values are exactly same, just that the numbering, this I'll use as bus 1 and this I'll use as bus 2 and this I'll use as bus 3. Now what is the Y bus? The system is same, just the numbering of the bus has been changed. So what is the Y bus? So again, begin by marking the Y12 is minus J10, just the reciprocal of this, and then Y13 is minus J5, just the reciprocal of this. Now 1, 2, 3, and then 1, 2, 3. So no matter where, how the buses are arranged, just look at the off diagonal elements first. So what is Y12? So this is minus J10. So it will be minus of minus J10. So this will become J10. And then what is between 1 and 3 you have this. So this will become J5. And this row will be copied here like this. Now is 2 connected to 3? So line 2 is not connected to 3 directly. So this is 0. And is 3 connected to 2? So no, it is 0. Now the diagonal elements, off diagonal elements have been completed. Now look at the diagonal elements. Add these two and then minus sign minus J15. Add these two minus sign minus J10. Add these two minus sign minus J5. So this is the Y bus for this particular system. This is the second example. So I hope you're able to get this. So let's solve slightly a bigger problem. So let me put some lines. This is example 1, example 2, and example 3. I'm going to do it now. Form Ybus for the following system. So, and the system network is something like this. So these are all buses. So you notice that there are 5 buses. So let me enter the bus numbers. So bus 1, bus 2, bus 3, bus 4 and bus 5. And there are different transmission lines like this. So 1, 2, 3, 4, 5, 6 lines are there. So this is a 5 bus 6 line system. So in fact, let's make it 7 line system. Where I'll add one extra line here. So this between the two buses there can be multiple lines, and this is called a double circuit line. These are all single circuit lines. This is called double circuit. In fact, double circuit lines are more common in power system. So even if one line is gone, we have the other line, and you can also find triple circuit lines also sometimes. Anyway, let's begin by I'll directly write the admittances. So minus J5 minus J10. So you should realize that sometimes impedance will be given in the question and sometimes admittance will be given in the question. How would you know whether it is impedance or admittance? So it will be mentioned in the question. Even if it is not mentioned, you can look at the sign. If it is negative, that means it is admittance, because you know that a transmission line will be reactive, so it will have positive impedance, positive reactance, and therefore if it is negative value, then you know it is admittance that is given to you. So this is minus J7, and for this line 2 4, the impedance is the admittance is minus J8, and for line 3 4 it is minus J3, and there are two lines here, and each line is minus J4 and minus J4. So again, I have the system data given to me. So the question is how to form the Y bus. So you can try it yourself. uh, you can pause the video now and form the Ybus, and then whereas I'll also be doing it now. So since the n is 5, this is the 5-bus system, so I'll have to have 5 rows and 5 columns for my Ybus. So this is row 1, row 2, row 3, 4 and 5. So I have 5 rows and then 5 columns. So column 1, column 2, column 3, 4 and 5. So let me also give the numbering. So now let's form the Ybus. So again we have our two rules. So let's look at off diagonal elements. So first row, second column. Is there any line between 1 and 2? Yes, there is a line. So minus J5. So it becomes J5. Is there any line between 1 and 3? No. Is there any line between 1 and 4? There's no direct line, and 1 and 5 also there's no direct line. So this row I can copy here, J5 0 0 0. Now let's look at the second row. Is there any line between, so I'm again doing only off diagonal elements. Is there any line between 2 and 3? Yes, there is a line between 2 and 3, minus J10, so it becomes J10. Is there any line between 2 and 4? Yes, J8. Is there any line between 2 and 5? Yes, there is also a line. So 2 is very highly connected one. 2 is connected to all of them. 1, 3, 4 and 5. So it has all these elements, J7. So I can copy this here. These 3 elements I can copy it here because Ybus is symmetric. That's it. Now let's look at the third bus. So is 3 connected to 4? Yes, 3 is connected to 4. So this element will be minus of this. So it will be J3. Is 3 connected to 5? No. So it will be 0. So it will be J3 and 0. Next, is 4 connected? Already you see it's taken care. 4 is connected to 2, 4 is connected to 3. So already it is taken care here. So J8 and J3. Now 4 is connected to 5, but there are 2 lines. So what you have to do? So if there are 2 lines, you know that if the impedance, parallel impedance will be, you can half of the impedance, and whereas this you can just add them. So minus J4 will become total admittance, that is minus J8, and then again it will become J8 because the minus sign you will have to remove. Now coming to the step 2, that is coming to the diagonal element. So what you have to do, add everything, J5 plus 0 plus 0 plus 0. So it will be finally J5 and add a minus sign. So just with a minus sign, minus J5. Again add everything. 5 plus 10, 15, 15 plus 8 is 23, 23 plus 7 is 30. So minus J30. So this is the Y22. So what is Y33? So Y33 will be minus J13 because 10 plus 3 is 13 and with the minus sign. Now 8, 16 plus 3, 19. So minus J19. And then 7 plus 8 is 15. So minus J15 is the impedance here. So finally, just by observation, I am able to write this. Now suddenly you might ask a question, why should I take the minus of this? Why should I take, what is the logic behind this process? I'm just doing mechanically the process and then finally I'm forming the Ybus. But what is the logic? Why I should take the negative of this and all these things? Refer to my previous 2 videos, you will know the logic. So this is just a numerical examples I'm doing. The entire, if you have not seen the previous 2 videos in this playlist in which this is there, you will not understand the logic. So, and basically what is the logic? Logic is nothing but just we are applying KCL at each node. Kirchhoff's current law at bus 2, Kirchhoff current law at bus 3 and all these things. It will form like this. Anyway, that's again, we are going back. So let's do slightly complicated problem, slightly a different kind of problem, where we have here there's no connection to the ground. So where we have some shunt elements, how to handle them? Let's do that. Okay, so this is example 4, and the question is form Ybus for the following system. Now, in this system, as long as this is a 3 bus system, bus 1, bus 2, and bus 3, the impedances are given, all impedances are per unit, you can form a 3 bus system easily up to this. But suddenly you notice that there is a generator G1 with its own internal reactance of J.2, and there is another generator with own internal reactance of J.5. So when such generator elements are given, how would you handle the Y-bus formation? So what you have to do is simply convert the generator into a Norton's equivalent. So what is Norton's equivalent? So just a brief Norton's equivalent. Just a minute. Yeah. So Norton's equivalent source is nothing but if you have a generator in parallel. I'm sorry. If you have a generator in series with reactance to a bus. So let's say this is generator, and then this is J.1. This can be converted into a current source in parallel with the same impedance J.1. So now what is the value of this I? It will be equivalent. So you should know some more details like what exactly is the voltage being generated. Then from that voltage I can just do that. So this is example from DC circuits. So if you have a voltage source, so let's say a voltage source of 20 volts whose internal impedance, let's say AB, or whose internal resistance is, let's say, 4 ohms. This can be equivalently represented as a current source. So this point is still A and this point is still B. So there is a current source and it is having a parallel resistance. So this is 4 ohms, and then this one 20 by 4, so V by R. So 20 by 4 is 5, so 5 amperes is the current, like this. So it should be 5 ampere current source. So a 5 ampere current source in parallel with 4 ohms is what we can do that. So what is the logic? So just look at open circuit voltage and short circuit current. So what happens if I open circuit A and B and measure the voltage? What is VAB? So under open circuit voltage, what is VAB? So if I put a voltmeter at A and B, so that voltmeter will measure 20 volts because there won't be any current. Ideally speaking, it's an ideal voltage source. So with zero current flowing in this, there's a zero voltage drop. So I'll have a 20 volts. So this is open circuit. Similarly here also, if I put a voltmeter between A and B, but this 5 amperes current is anyway flowing, circulating in this. So 5 into 4 is 20 volts. Voltage is dropped across this. So that voltage is measured and I will also get 20 volts here. Now let's look at short circuit current. What happens if I put an ammeter? So this is an ammeter and then I short circuit this. So the ammeter will read 5. So this is IAB current short circuit. It will be 5 amperes. And the same case if I short circuit this with an ammeter, and the ammeter will also read this. No current will divert to 4 ohms because this parallel path is completely zero resistance. So entire 5 amperes will flow, and it will also be 5 amperes. So both these two circuits are behaving exactly the same way when I connect an ammeter or when I connect a voltmeter. That means under open circuit voltage and short circuit current, both are behaving same way. So they are equivalent. So that's basically the Norton's equivalent. So this concept from DC circuits, we are borrowing it into AC circuits, and then we are doing this Norton's equivalent. But anyway, the value of how much voltage this is being generated at G1 and G2 is not given. So therefore, I just simply put I as a variable. So if it is G1, then I'll say I1, and then I'll do that. So let me redraw the main circuit. So if I just copy this circuit, so what I'll do now is I'll just simply delete this part and also delete this part, and then I'll show it as a parallel current source. And similarly, I will again show it as a parallel current source. And this value will be I1, this value will be I2. Basically, this is the external current being injected into bus 1. Now, this J.2 and everything, they are all in impedances, so you convert into admittances. So what is Y12? So it is 1 by J0.09. So let me use my calculator to do that. So 1 divided by 0.09I. So I'll get 0 minus 11.11I. So this is minus J 11.11. So what is Y13? So 1 divided by 0.04I. So I'll get 25. So minus J25. And this minus J20 it will be, because 1 by 0.05 will be J20. So this is Y32. Similarly, convert this also into admittance. So 1 by J 0.5 will be minus J2, and 1 by J point will be minus J5. Is it 0.2? I think if I go up. Okay, so the value is 0.2 given. Now, what is the, if I want to write it, so you know that I1, I2, I3 equal to Y11, Y12, Y13, Y21, Y22, Y23, and then Y31, Y32, and then Y33. And then I have V1, V2, V3. So this is simple uh, Ohm's law. So current is nothing but admittance into voltage, and this is the current injection vector. This is your actual Ybus, and this is the vector of voltages at all three buses. Now you notice that this current, what is the current in this branch? So here the voltage is 0 and here the voltage is V1. So what is the current here? So let's call this as I10. So what is I10? Current in this branch. So it's nothing but the admittance J5 multiplied by V1 minus 0, or it will be minus J5 into V1. So this current is also a part of I1 current. So if you look at the KCL at bus 1, so I1 current is coming like this. I1 current is injected. Some current is going down. Then the remaining current will be I12, and then the other current will be I13. So therefore, this element. So what is I12? I12 will be V1 minus V2 multiplied by minus J11. So that element will come here. So and so on. So you had seen that this. So the only adjustment that we'll have to do will be in the diagonal element. So where this thing is there. So let me now suggest rule 3. Already rule 1, rule 2 we had given. So rule 3 for shunt elements. at bus K. So imagine that there is bus K, and there is rest of the circuit, everything is going on, but then there is a shunt element, and this is YK0. This is the notation, and Y means it is admittance already. Shunt element at bus K with admittance of YK0. So this is small YK0. So what is the thing we have to do? So the current will be VK into YK0. So update YKK. So basically YKK is nothing but the exist earlier YKK, and then you will have to also add this element here plus YK0. So but then this element, since it is Y, and if you are talking about shunt reactance, then the shunt reactance admittance will become negative, and that will anyway, this YKK is already negative, so it will just add to that. Anyway, so regarding sign, you just look at the problem that we are now solving, you will understand it. So anyway, let's come back to this. So I'm just getting a feeling that I'm over expanding this. So we could actually solve it just by observation. Anyway, we'll also do that in one more problem. So let's now look at it. So I think I'll make one more copy of the figure just for your convenience. So this is one, bus 1, bus 2, and bus 3. So what are the values I have? Minus J 11.11, 25, and 20. Minus J 11.11, minus J 25, and minus J 20. And then here I have shunt admittance minus J 5, if I remember. Yes, and then minus J 2. Minus J 2. I also have I1 current, which we don't worry right now. And then I also have I2 current, which we don't worry right now. So from this, so I'll just form the Ybus. So let's look at off diagonal elements. So between 1 and 2 minus J11, so it will become minus of that, so J11.11. Between 1 and 3 minus J25, so it will become J25. So these two I'll copy it here, J11.11 and then J25. Now look at the second row. 2, 3 is the off diagonal element. Between 2 and 3, J20 minus J20 is there. So it becomes J20. So it becomes J20. Now coming to the diagonal elements. So if I add these two, so this will be 36.11. But then I should also add J5 to it. Or in fact, I have to first add these two and then also add minus J5. So actually what happens here is minus J 36.11. So I add these two, change the sign, and then I'll add J5 to it. So finally it will become 41.11. So this is equal to minus J 41.11. So that's it. Next, let's look at the other cases. So bus 2, 20 plus 11.11, this will be minus J 31.11. To that, minus J2, I'll just add it. So it will become minus J 33.11. So this is the final value. And then what about this element? So here there's nothing, no shunt element connected. So I just add these two, 45. So it will become minus J 45. That's it. So this is my Y bus for the system. So Let's do one more problem so that it will be of the similar kind, so that it will be very fast. So, okay, now let's look at the example 5. So in this example 5, what I'm doing is it's a simple two bus system, it's just one line, and all admittances are given. So, sorry, not admittances, impedances. Impedances are in per unit. So that means J.16 is the impedance between line 1 2, and this is the impedance of the generator. So there is also a load given which is zero point 0.5 plus J3 per unit. So by the way, you notice that everything we are solving in per unit, because that's why per unit is a topic which is just studied before forming Ybus. Now what to do with the load? So there is a decision actually. So either you can say consider load in Ybus, or uh, just leave out, don't consider loads. So we'll follow the second case. You just don't worry about this load. If you know the equivalent impedance of this load, then that impedance you can model it as a shunt impedance, and then you can do that. But for the time being, that information is not given. Just the load value is given. So therefore, we don't worry about this. We just simply leave out the load. You just mention that, and then now this one we already know. You can convert it into this. So if I convert into admittances, so then this will be 1 by j point minus j5, and this will 1 by 0.16, so it will be minus j6.25. So if you do 1 by 0.16, you get this. So from this, I can build the Y bus. So Y bus will be something like this. Only 2 by 2 matrix, 1, 2, 1, 2. So this first row, second column, so I'll get, so this minus will be not there, so j6.25. And this I'll copy here, j6.25. Now diagonal element, I just add everything, so with a minus sign, minus j6.25, and then minus j5. So this is there. So total it will be minus j11.25, but then I'll just write that here, 11.25. What about this? So at bus 2, this I am not considering at all. So you just, for the timing, simply ignore this. So I'll just have minus j 6.25. So this is the bus admittance matrix for the above system. Let's do more problem. So I'll write example 6. Now in example 6, we'll considering line charging susceptance, or in other words, pi model of transmission line. Form the Ybus. So let me explain what I mean. So it's a simple 3 bus system again I'm taking. So this is bus 1, bus 2, and bus 3. And I directly say minus J10, minus J6. So these are the admittances already given in per unit. But this transmission line has a pi model. So this is a pi model transmission line. So you know what is a pi model for a very long transmission line. Uh, Not only that it has reactance, it also has some kind of capacitance to the ground, because it's a high voltage line and there is a zero voltage on the ground. So two different voltages separated by the air in between act like a capacitor. So that is the pi model of a capacitor. So this is also a parameter of this particular line. So the total capacitance of the line in pi model will be divided half and half here. So this is called B by 2 and B by 2. So B by 2 and B by 2. So B by 2 is like a parameter that is given. So, so let me write it in the form of data. So line 1, 2 and then 2, 3, and the B by 2 will be the susceptance. So now what is a unit? So you can see, because it's a capacitance, so it will be minus J something. But then if I want to show it as a admittance or susceptance, then it will again be the reciprocal of it. So typically the capacitance value will be negative. So let's say minus J2 or something like that. So then it becomes positive uh, after converting into admittance. So since anyway in the circuit I'm drawing admittances, so I don't want to do that. So here just take J2, J2. So the total is J4. So here again J1 and J1. So just remember that the line charging susceptance will be like a positive J connected like this. So J2 and J1. So you distribute it on either side. Now looking at this, I can again form the Ybus. So Ybus will be again 3 by 3 matrix. So it will have 3 rows and 3 columns. So first off diagonal elements, so 1 to 2 minus J, so minus of that, so it will be J10. 1 to 3 no direct line, so copy this. 2 to 3 J6, J6. Now coming to the first one, so it will be minus of J10, then I'll have plus J2. So this is the difference. So finally I'll get the value. So let me just write it neatly here. Minus J10 plus J2. So finally the value will be minus J8. Similarly this one. So 10 plus 6 is minus J10 minus J6. Then there is a J2 is plus and J1 is also plus. So plus J2 plus J1. So total this will become 16 plus 3, that is minus J13. And here it will be minus J6 plus J1. So that's only care we need to take about the signs. So finally this is my Ybus for this particular system. So I hope now you get how to handle the line charging susceptance. Okay, so we have been doing a lot of problems. Let's do one interesting problem which typically you don't find, in regular textbooks. That is solving a simple DC circuits using the Ybus concept. So the question is like this. So it is example. I think it is example number 7. So the example number 7 is find the node voltages using Ybus for following circuit. So I'll just draw the circuit. So the circuit is actually a DC circuit. So this is the circuit, and let me mark the nodes. So the nodes are, let's call this V1, let's call this V2, let's call this V3, and let's call this V4 and V5. And this node I would consider it as a ground. So of course you can consider this as ground or this as ground, anything. So just it happened that in the question it is given. So this is V0. So it will be 0 volts. What about the values? So this is 20 volts. This is 8 volts, and this is 15 volts. And what about the resistances? 2 ohms, 1 ohm, and this is 5 ohms, and this is 8 ohms, this is 6 ohms, and this is 4 ohms. So let's try to use Ybus, and then at least I want to show, my point is I want to show there are practical applications of forming Ybus, and in this example we can use Ybus to solve the things. So this is let's take as 8 ohms. Okay, so what is the first step? So step 1 is use Norton's equivalent. So if I use Norton's equivalent, so basically the question is what is V1, V2, V3, V4, V5. So this is the question. So this is what we have to find out. So I already know that V1 will be, see from here if you see, I'm increasing from minus, I'm going to up, it will be plus 20 volts. But then some voltage drop here, then what the V1 will be. So slightly V1 will be slightly less than 20, assuming the current direction is like this. But whatever. So after solving this circuit, we will come to know everything. Now you can form nodal equations and then all these things, you can find that. But let's do using Ybus now. So first step is use Norton's equivalent. So if I use Norton's equivalent, then there are 3 voltage sources. I can convert them into current sources. So I have, so I'll draw like this: 4, 2, 8. This is also 8, and then so this is my circuit. So this is the branch, and here I'll add a current source, and here I'll add a current source. So also notice I'm giving the direction properly. Let me see. So yes, so this is node 4. So actually this should connect to node 4, but anyway it is understood. So this is also another current source. So my question is, what are these values of these current sources? So here 15 by 5 is 3 amperes, and here uh, 8 by 8 is 1 ampere, and here 20 by 4 is 5 amperes. So I have like this. So you notice that as a result of having this using the Norton's equivalent, so this is node 3. Node 3 is receiving 3 amperes, whereas node 5 is losing 3 amperes. So this is node 4 is receiving 1 ampere, and this is node 0. Node 0 is actually losing 6 amperes, and node 1 is receiving 5 amperes. So like this, node 2 is not receiving anything. So therefore if I once again copy this circuit, so what I'll do is I'll just remove all the voltage sources. So then I'll just remove all the voltage sources. Connect this, connect this, and connect this. And I have this external current entering this node V1, and the external current is 5 amperes. And I have at node 2 nothing. At node 3, external current of 3 amperes is entering. So just this one. And here the current is leaving actually. So I put the arrow direction reverse way, or let me just maintain the same direction. But what is this current? It will be minus 3 amperes. Similarly, at node 4, 1 ampere is entering. So at node 0, actually minus 6 amperes are entering. but this doesn't show up in the equation, so not required. Also convert everything into admittances. So what is 2 ohms? So 1 by 2 ohms will be 0.5 mhos. I hope you know this unit, MHO. So 1 MHO is 1 by 1 ohm. So the reciprocal of ohm is mhos, and the symbol is like this. What is 1 by 4? So it is 0.25 mhos. 1 by 8 is 0.125 mhos. 1 by 6 is, what is 1 by 6? We calculate that. 1.6. So 1.6 mhos. Let me just confirm 1 by 8, 0.125. 0.125 mhos. This is 1 mho and this is 0.2 mhos. So I have all this thing. So now I can make the Ybus. What is Ybus? So how many nodes are there? So 1, 2, 3, 4, 5. This node doesn't count. This is like a ground. So I have 5 nodes. 1, 2, 3, 4, 5. So let me draw the lines also. Now the values. So between 1 and 2, 0.5. So I have to use a minus sign for that. So minus 0.5. So earlier the j used to be there. So therefore this used to become positive, but now it is negative. Between 1 and 2. Between 1 and 0, okay, we'll do that later. 1 and 3, nothing. So 1 is not connected to anything else. So all these things will be 0, minus 0.5, 0, 0, 0. What about 2? 2 is connected to 3, so minus 1. 2 is connected to 4, minus 0.125. 2 is not connected to 5, so 0. So minus 1, minus 0.125 and 0. What about third row? So 3 is connected to 5, not connected to 4. So this is 0 and minus 0.2. 0 minus 0.2. What about 4? 4 is connected to 2 that I already considered. 4 is connected to 5, 1.6. So minus 1.6, minus 1.6. Now coming to the diagonal elements. So 1 is connected to ground, 4 is connected to ground, rest of them are not connected to ground. So I'll just add everything. So 0.5, it will become plus 0.5 and then plus whatever is admittance, 0.25. So 0.5 plus 0.25 will be 0.75. So I'll write that here, 0.75. Here 0.5, 1.5, and so just addition of all this. So just my rough work. So 1.625. Okay, and this is 1.2 and this is 0.125 and then 1.6. So 1.725 and this one will be 1.8. So this is my Ybus. Now what is a current injection vector? So what is I? So the current injection vector will be I1, I2, I3, I4. So external current entering node 1 is 5 amperes. External current entering node 2 is 0 amperes. External current entering node 3 is 3 amperes. External current entering node 4 is 1 ampere. External current entering node 5 is minus 3 amperes. So this is how we defined IK. So now I have I and Y. So now the next job is to find V. So we know that I equal to Y bus into V. So therefore, what is V? So V is nothing but Y bus inverse multiplied by I. So I know Y bus, so I can invert it and multiply with I. So how to invert a 5 by 5 matrix? Of course, you have to use a computer. So let's do that. I go to my MATLAB interface. So I'll directly enter here. So I is my I matrix. So I vector. So it is 5, 0, 3, 1, minus 3. So 5, 0, 3, 1, minus 3. So this is the vector. So if I just, so 5, 0, 3. So I'm getting the I. Now let me define Ybus. So Ybus equal to, so what's in my first row? 0.75 minus 0.5. 0.75 minus 0.5, then 0, 0, 0. Minus 0.5, 1.625. And then minus 1, minus 0.125. And finally 0, I think. Yeah. So 0, minus 1, 1.2, 0, and minus 0.2. So 0, minus 0.125, and then 0 and 1.725. I'm sorry, 1.725, and finally minus 1.6. So I hope I'm not making any mistakes in typing the data. So minus 0.2, minus 1.6, 1.8. That's it. So this is my Ybus matrix. So let me quickly check. And 0, 0, 0, minus 0.5, 1.625, 1. It's always good to cross check because you might make some mistake somewhere. So it is good to check. I'm just checking it. All right. So now I think this is all correct. Okay. So what is V? So simple. V is nothing but I and V, inverse of Y bus multiplied by I. So let's suppress the display of this. So finally I'm getting the voltages. So from solving from MATLAB, so I'll get, so this is V. Sorry. I don't know how these lines are coming. But anyway, so this is my V. I'm sorry. So we were expecting V1 will be something less than 20, but I think here it is 24. That means from this we understand that the current will be in the reverse direction. So you can verify this using your regular network solutions. So 24, 26, 27.573. So after solving this, I got 24 volts. This is 26 volts, and so on. So that means there's a 1 ampere current flowing like this. So whatever. So just verify this, and if there's anything mistake, you can let me know. So this is just an example to show how Ybus can be used in solving the circuit. Something similar we will also do in AC circuits, which we'll see in the power flow problem. So with this, I'll conclude the topic on Ybus. So try to see last 3 videos of like this is a 3-part video, I think, bus admittance matrix. So this is just That's about Ybus. So after seeing this, I hope you should be able to uh, prepare the Ybus for any system that is given to you. Thank you.